Okay, so we've been talking about random versus fixed factors, and hopefully you have a little bit of clarity on that, although that is a nuanced idea that will take some time to develop. We've also been talking about crossed versus nested. Gary says it's a lot of fun to think about that. You may or may not agree here. I think it's challenging, and I think sometimes what's hard about it is that it depends on the experimental setting in which you find yourself. So sometimes you can't just say individuals are always random and they're always nested. Well, when you're talking about individuals that are non-replicable students in a classroom setting, then they're probably random, yes. And they're probably also nested because they're nested within a classroom. But I could think of other cases where students would be fixed and crossed, perhaps. That would be unusual, but it could happen. So I think it's a challenge to do. And well, Gary agrees. He says it's also very challenging. So you're going to get a lot of practice. The first way that we kind of practice this, I've really emphasized this procedure a lot in the past, and I'm perhaps going to emphasize it a little bit less this semester. I sometimes wonder about the worthiness of it. I think it's essential. If you're a statistician in this class, you've got to understand this. This is a very practical skill, what we're getting ready to do. If you're not a statistician, it's probably less important, I'll be honest, okay? So when we model an experiment, we have to think through these different factors. Gary has them listed here. First, think about your sources of variation. What are the things that would affect the heterogeneity of your response variable? The things that change it, make it change, in other words, okay? So determine those sources. Those may be fixed sources, they may be random. Just list all your sources out. Make a complete enumeration of all those sources. Then you think about which are crossed and which are nested. So if you have students nested in a classroom, make note of that. I draw pictures a lot, especially when I'm talking with applied scientists. I draw a lot of pictures to show the difference between the crossed and nested. And maybe as you're learning this, drawing a picture of the factors and how they interact, it would be really useful. And that's going to relate actually to what we do next with the Hasse diagrams, okay? Then figure out, think through, for this context, which of these factors are random and which ones are fixed, and decide at that point. Then define which possible interactions you have. Okay, obviously, only certain types of factors are allowed to have interactions. Okay, so make sure you do that clearly and conceptually sound. Okay, so now we're getting to this new idea that I think is a nice way to represent all the terms in your model, and it's called a Hasse diagram. It's an old idea. Actually, this comes from more mathematics, the Hasse diagram. They use it in combinatorial mathematics quite a lot. But it's just a graphical representation to help you keep track of your terms in your experimental design model, okay? In old school analysis, i.e., when we used to use the sum of squares approach for doing the analysis, the Hasse diagrams were essential for defining your mixed and random effects model. So remember, like if you had a random effect using the old school method, the non-Rimmel method, you could get like weird negative variance estimates and things like that. And we just arbitrarily set them to 0. Back in the day when I first learned this, I actually did that a lot, believe it or not. Even though we had Rimmel analysis, it still was kind of new-ish, okay? But we're gonna emphasize Rimmel, the restricted maximum likelihood approach here. So the diagram is not so central. So that's why I said maybe it's not so essential for all of us to know, but I think it's really illustrative of how these models, the terms relate for statisticians to understand. I have a real bias that I think it's important for the statisticians to really understand this. So a Hasse diagram is just a graph of nodes, and it has, each node is a term or a factor in your model. The nodes are connected by little line segments, just lines, that illustrate relationships between the nodes. So it might show nesting, meaning you'll have one node right below another node connected with a line segment. Or it might be crossing, which I'll show you what that looks like in just a moment. Gary talks about incomplete Hasse diagrams in the notes, where each node is just given a label for some term, and then an indication that that term is random or not is given by a parenthesis surrounding that term. Okay, we'll do the same. I like the way Gary does this in the book, so I think I'll stick with his notation. A complete Hasse diagram will also include the subscripts that indicate the number of levels and the degrees of freedom. Sometimes I'm a little lazy and I just don't include all of the, like the number of levels and degrees of freedom. But for your first few times, I think it's really informative to think through all of that. And sometimes you find mistakes in your thinking by doing that. So here's an example. First example. We've got two factors, A and B. A is random, so noticed in the Hasse diagram, the random factor is denoted by the parentheses around the factor name, and B is fixed, so no parentheses. When we cross it, so we've got a random term crossed with a fixed term, and when we cross it, we know that that interaction between A and B is going to be random because A is random, so that kind of trumps it, right? And then nested within that A-B interaction is the error, the random error, because the random error is specific to that unique combination of A and B. Now, why do we have an interaction between A and B? It's because we can fully enumerate every level, every treatment level combination between A and B, okay? By the way, what is that M at the very top? Any guesses? Take a moment to consider, but it's just the grand mean. So you remember we write out our model, and let me add an illustration here. So we write out our model typically, oh, let me stop this and get this to, I can't get my pen to work, so I'll skip it, but write out your model like Yij equals mu, the mean, and that's M, plus alpha, I, beta j, alpha beta ij, epsilon ijk. Okay, so if you write it out, then you can really see how all of the terms are included in this diagram here, the Hasse diagram. Here's something a little bit more complex, I'd say. Which ones are random? Well, we've got the grand mean, of course, but which ones are random? Well, we know A and B, right? C is fixed. All two-way interactions are random, and the three-way interaction is random. The error, of course, random by default. Notice what ones cross. Well, we've got lines allowing interactions between all three levels, or all three treatments, or factors. So everything crosses. No nesting, except for the error. Notice the crossing of the two-way interactions creates the three-way interaction. It's not like a weird cumulative effect. We actually do sometimes count how many terms. We'll get into that later. But when we cross the AB, AC, BC, we get ABC error, or ABC random effect. Okay? Another. Well, this looks really weird. Let's look at the diagram and see if we can diagnose it. We've got the grand mean, a fixed factor A. Okay, that makes sense. But then right below A, we have a random factor B. There's no crossing, and it's not at the same level. So B is nested within A. Okay? Then you go down further. C is right below B. C is nested within B. And then we've got the error contained in C. So everything's nested. C nests within B, B nests within A. A is the only fixed. So maybe this is a curriculum. So we're evaluating the effect of a curriculum. And that's our fixed effects. It's the thing we really want to know about. But we've got a level of B, teachers who implement the curriculum, And we can't replicate the teacher's teaching from year to year, so we make that a random effect. And then we have students within the classroom. So teachers are nested within the specific curriculum from which they teach, because they only teach one curriculum, and they're assigned a curriculum when you teach in public schools. And then students are assigned teachers. So everything's nested in a scenario where A is curriculum, B is teachers, C is students. Okay, here's something a little bit different from that even. Got our grand mean, and then we got two fixed factors, A and C. Do they cross? Yes. A and C are fixed, and they cross. Okay? But then we have B here. What is B doing? It does not cross with A, and you can tell that because there's just a simple line segment going down to B directly from A. Okay? So B is nested within A. But B and C cross. So it's a little bit wonky, the diagram here, I always feel like. But it makes sense to do it this way, okay? Because the B does not cross with A, but it does cross with C. So it's actually a lower level interaction in the model, and it's going to be random because B is random. You could even make this a straight line now that I think about it conceptually. That would make sense too. And then we got the error, of course, as always. So think about a scenario where this could take place. Maybe A is still the curriculum, and C is, I don't know, the student cohort. Not the students themselves, but like the background of the students. Some characteristic of the students. Like whether or not, for example, whether or not the student knows English as their primary language is C. Okay, so you could have a crossing between the curriculum choice and whether or not English is the student's primary language. But then you've got the teachers, B, nested within the curriculum choice. And then you've got the teacher versus is their primary language of the student in the class, students in the classroom, English or not. And that can cross with the teacher. And that makes sense, right? Because maybe teacher to teacher heterogeneity has an effect on the whether or not the classroom is assigned to be an English first classroom or English learning classroom. And then we've got the error. Okay, so I'm going to leave you with this exercise, and then I'm almost out of time on the video, so I'll stop. But I like this one because I love cheese. We have 4 different kinds of cheese, cheddar cheese here, and we've selected 10 students at random, some with a rural background and some with an urban background. Each student will rate for bitterness 8 bites of cheese, 2 of each of the 4 types, and it's going to be randomized. This sounds a little bit like an experiment we've been talking about. So think about that. See if you can draw your Hasse diagram.